All right, I will begin with a word of prayer. All right? Heavenly Father, we thank you for this day. I thank you for these students again and for your many blessings to us each and every day, Lord. You know I pray. Amen. Okay, so it was just asked me, does this quiz problem make any sense? Because you didn't give me the time. So like I basically told you that the angular acceleration was what? Or I didn't tell you that. All right, so suppose you knew that the angular acceleration was like 20 radians per second squared. And did I not? Oh, I did. And suppose that the initial angular velocity was 10 radians per second. Then I could say find omega f at time t. See, this question makes sense. You don't actually have to know the time to give an answer. There's an algebraic answer that can be given here. And that answer would be as follows. So WF, the final angular velocity, is equal to the initial angular velocity plus alpha t. So with what I have written here, the answer would be 10 radians per second plus 20 radians per second squared times t, and that would be the answer. The answer would just have a t in it. But that's not what I intended for your quiz. There's actually a typo in the quiz. What part was it? Part B of which one? Quiz 5. 2B. I meant to say t equals 210 seconds. You can see that that's what I was thinking about when you get to like part D, right? I say 0 less than t less than 10 down there. My mind just skipped and I didn't write the 10. But in my defense, the question would still make sense without the 10. Okay. Do you guys have other questions? Let us do an interesting problem. Let's calculate find the kinetic energy of a rotating barbell. So here's what I have in mind. We have a sphere, another sphere, right? They're connected by, a rod here. And so we're ignoring the subtleties of how the bar actually enter. You're going to treat it like there's two spheres in a rod of a particular length. I'd like to calculate the kinetic energy from taking this and rotating it. So any of you happen to have a barbell on you? Anyone bring one to class? How about like one of those little exercise weight things? So, how am I supposed to illustrate this then? Oh, there it is. So the question then is, I'm going to rotate this thing. And so the answer to how much kinetic energy this will have for a given angular velocity will very much depend on where the rotation is around. All right? So let's, let's see here. So you guys want to rotate it around the middle? How about that? Yeah? So let's suppose that we're rotating it like that with angular velocity omega. So you can imagine twirling it round and round. I mean, I can't quite imagine that, but what's the kinetic energy of such a thing? So I need to know a couple different things. I need to know the mass of these guys, and I also need to know the let's say m little mass of the rod. All right. Oh goodness, I'm forgetting something, guys. I'm sorry. Do they have their textbook on them? I need to look up the statement of something. Actually, I may actually soon find that what I'm about to tell you is forbidden. I don't know if it's actually forbidden or not. There's something called the parallel axis theorem. And it just occurred to me that my assumption that it's in your textbook may be incorrect. Let's check on that right quick. Parallel axis theorem. Okay, never mind. Not a theorem in your book, unless it's hidden in a paragraph of text somewhere without a reference in the index. So I think we're going to have to make do with what is given to us on page 210 of your textbook. There's a table of moments of inertia here, and as such, I can't do this problem the way I wanted to do it, so I'm going to have to simplify it a little bit, all right? So let's think about the barbell in a kind of silly way. So it's not really as much of a barbell. It's really more like a long, thin rod with a couple of really small weights at the end of it. So we're going to neglect the size of the. We're going to think of these balls at the end of the rod as essentially just. We don't really care about how big they are. We're going to neglect anything having to do with how big the end masses are. And on the other hand, we're going to suppose that the system is being twirled around an axis like this, all right? So, if you, and so that we have a thin rod, and let's let the mass of the rod here be equal to m2. And so we're spinning it with angular velocity omega. The question is, how much kinetic energy does such a thing have? So in order to answer this question, I have to determine what's the moment of inertia for the system. Okay, so there's a couple. The moment of inertia comes from three things in this problem. All right, so what's the moment of inertia here? Inertia is equal to the moment of inertia for the left mass plus the moment of inertia for the rod plus the moment of inertia for the right mass. Okay? Now, if the other thing I need to tell you in order for this problem to make sense is we need to know how long the rod is. All right? So let's suppose that the length of the rod is L. Okay? So this distance is L. If you think about it, the longer L is for a given angular velocity, like the more kinetic energy you're going to have, right? If you have a really, really long rod and you're rotating it at a certain rate, that means the balls are whipping around pretty fast. If the rod is shorter and you have the same radians per second, then you're comparatively speaking, having a lower speed, right? All right. Great. So what's the moment of inertia for masses? Well, the moment of inertia for mass is m times the distance the distance from the axis of rotation squared. What's the distance? So this is one of our rules. If we have an axis of rotation like this, right, this is my axis of rotation, and if I've got a mass m out here like that, whatever that distance is, let's say r, the moment of inertia for m is just mr squared. So this is the moment of inertia for a point mass. All right. So the moment of inertia for the left one, what's the distance from the axis? I'm assuming that we're in the middle of the rod, so how far is that? If the whole distance is L, what's this distance? L over 2, right. So I have to, that's my R, so to speak, L over 2 squared, plus the moment of inertia for the rod, which I'll fill in just a second, plus the, well, over here, m times again L over 2, because the other side is also the same distance away. So what's the moment of inertia for the rod? Well, that, I got to go to the table, all right? And if you look on here, part F of the table on page 210 tells us that for a long uniform rod of length L, the moment of inertia, if you twirl it around its midpoint on a perpendicular bisector to the midpoint, the moment of inertia is 1/12 ml squared. So we got a 1/12 and m2 L squared. All right, so we can put this all together. We got 1/4 ml squared times 2 from, the outer 2. And then plus a 1/12. Can you see how to simplify that, like algebra-wise here? I noticed that we've got an L squared on everything. We can factor out L squared, right? And so what we have is 1/2 m plus 1/12 m2 times L squared. That's the moment of inertia for this system. Okay? And then what's the kinetic energy for the rotational system? Once you figure out the moment of inertia, the kinetic energy is, assuming that it's just rotating at rest, right? If I was to take this rod with the two balls like that, and to take it and throw it round and round and round like that, then it would also have translational kinetic energy, and I'd have to account for that as well. But I'm saying just take it and rotate it at rest around an axis, a fixed axis. So there's only rotational kinetic energy, right? And so the kinetic energy is just 1/2 I omega squared, which is precisely, 1/2 of 1/2 m plus 1/12 m2 L squared omega squared. And without putting numbers in, that's kind of like the best kind of answer I could give you for this sort of problem. Let's look at a different problem that's kind of like this, but a little bit different. And it's more like one of your quiz problems, so maybe it'll help you. So I want to talk about how to find the moment of inertia of, well, actually, let's do something a little more interesting. This one's going to be a problem of dynamics, so I'm going to talk about the Atwood machine. But this time, up here, we'll put a pulley that's formed with, it's got a reinforcement of 2 cross pieces like that. And then there's a rope that pulls over it, and you got mass 1 on one side, and you got mass 2 on the other side. Let's assume that the radius is r, all right? And let's be a little bit more numerical here. We'll say the radius is r is I don't know, say 3 centimeters. I don't know. I'm not sure really putting numbers in here really helps us that much. But what I want to say is that there's this wheel here, the pulley. It's made of two things. All right. It's basically a. If I were to expand that picture more, it looks something like. I can draw it. It's debatable. Very debatable. Let's see here. So what I'm trying to say is, and then inside there's the if that makes sense. I don't know if it makes sense. What I'm trying to say is that the wheel is formed by taking a strip of metal like this. You know, it's got some thickness, whatever. The thickness is pretty small though. And just taking that and bending it into sort of a hoop, right? And then you've got a couple of rods inside it that keep it together and allow you to anchor the center point on some pivot, you know, on some pivoting thing. And then, of course, the rope goes over the wheel, and it sticks to the wheel. The rope turns with the wheel without slipping. All right, it's a situation here. So to go further, I should tell you that the mass of the metal is, let's say, 2 kilograms, and let's say each one of these sticks, the sticks, the spokes, if you will. Each spoke has mass m equal to, let's say, 0.3 kilograms. All right. So you have 3 kilograms. 0.3 kilogram spokes, and the mass of the iron on the wheel, on the exterior part of the wheel, is 2 kilograms. And these are connected together, manufactured together, such that they rotate around a center point, and so doing form a pulley, right? Because it can spin and the rope goes, okay. So the question then is, what's the acceleration of the system? All right, that's the question I'm asking. See, because this is an Atwood machine, right? But the difference with this Atwood machine and the previous one we looked at, right, is what happened. What last time we did this problem, what did we say about the pulley? We said assume the pulley is essentially frictionless, but more importantly, massless. We're still going to assume that the pulley is frictionless. Like, we're not going to try to add some kind of like sticking to the where it's attached like that. No, I'm not going to do that. But we cannot assume that the pulley is massless. Now the pulley has mass, and so in order to accelerate the system, we must also accelerate the mass turning around a central point, which is to say that we must give the pulley itself an angular acceleration, right? So we can talk about a couple different things. One of the things we can talk about is the angular acceleration, alpha, of the pulley around the center point. So we have that angular acceleration. How is the angular acceleration related to the linear acceleration a? So let's, just to keep things relatively simple, let's assume that m2 is greater than m1, all right? So it's going to be, you know, falling this way, and so we'll take this as the positive direction, as to not confuse people. And what else can I say here? Yes, how are alpha and a related? So if the string is going over the pulley without slipping, the relation is that a is equal to alpha r. All right? That's just like, what are the other relations that are like this without slipping? Without slipping conditions, you have this one, before this, of course, the first one you have is that arc length is equal to what? R times theta. And beneath that, you have that omega, or rather that the tangential velocity v is equal to r omega. Well, this is just the next one up the chain. The acceleration is equal to angular acceleration times the radius, if there's no slipping. All right. So how do we solve this problem? There's three things going on. There is the torque on the pulley. There is Newton's second law on mass 1 and mass 2. Let's start out with the easy part, right, which is the Newton's second law. Also, we've got to be careful about the tensions here. So this would be maybe tension 1, and let's say that this is tension 2. You have the same tension like here and here. All right? So, Newton's second law, we have M1A equals to what? T1 minus M1G. See, because gravity is acting opposite the tension force, right? And let's see here for M2, we have M2A is equal to, well, M2G minus T2. The third thing, which is new, is we also have to think about the sum of the torques on the pulley. So what's the net torque on the pulley? So we have the inertia of the pulley, right, times alpha is equal to the net torque on the pulley. And so there's some things to unravel there. First of all, it's not immediately obvious what the moment of inertia is for the pulley. We need to kind of deconstruct that and work it out. But the other thing is, what's the net torque? Maybe we should do that first. What's the net torque on the pulley? Why is the pulley getting twisted? So you look at it, right? There's two things that are if I blow it up, a picture over here, right? I need a picture. I'll put it up here. So if you look at the pulley, right? We've got, this is the positive alpha direction, right? So T2 is like that, right? And T1 is like this. And those are being applied where? A distance r away from the pivot point. So what's the net torque? The net torque is RT2 minus RT1. So I'm using remember that formula we wrote down last time? The torque is equal to RF sine theta. Well, when the theta is 90 degrees, it's just the radius arm times the force. This is the best case, right? Best case possible. We're applying the force perpendicular to the radius of the turning, so we get max torque. And you see why one's plus and one's minus? Does that make sense? So the T1 is trying to make a rotation like that. Do you see it? So that's why this gives a positive torque, but that one's opposing it. It's trying to make the pulley go the other way. So that's why we got a minus here. All right? Incidentally, look at this. We could also think about this saying alpha is equal to A over R, right? So if you look at this equation that we just got to, one thing we could do would be just to divide this equation by the radius. What would that tell us? We'd get the moment of inertia for the pulley times alpha over R. What's alpha over R? It's A, right? So this moment of inertia for the pulley times A is equal to the difference of the tensions. Like that. Like this gets to that. Now, I like this equation because if you look at this one, and you look at that one, and you look at that one, if you look at these three equations, you might be able to see how to do the algebra there. Right? Because we're not really interested in what T1 and T2 are. We'd like to eliminate them. Right? So if I see what happens if I add, let me name these equations 1, 2, and I'll call this one 3. What happens if you add equations 1 and 2? We've got M1 plus M2. I'll factor out the A from the left-hand side. And on the right-hand side, I've got M2 minus M1 times G plus T2 minus T1. Oh, T1 minus T2. I can't read. Do you guys understand what I just did there? I just took these two equations and I added them. Right? Add the left-hand side to the left-hand side, add the right-hand side to the right-hand side. So we get M1 plus M2A on the one side, and we get, the difference of the masses M2 minus M1 plus T1 minus T2 on the right-hand side. Does that everybody track what I just did there? Okay. Oh, but look at this. Then we can do what? We can trade. That's almost this, isn't it? See that? This is actually then going to just be what? Minus the moment of inertia for the pulley times A by 3. So therefore, M1 plus M2 plus the moment of inertia for the pulley that seems wrong. Huh. 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 Oh, duh. What's alpha equal to? Well, this doesn't make sense from dimensional reasons. I know I've made a mistake somewhere, guys, and so this is an important thing for me to, come across from time to time, because it's important for you to know about this too. When you make a mistake, you can also use this. I've got mass plus moment of inertia. What's moment of inertia? It is a kilogram meter squared. That's its unit. See, over here, moment of inertia, mr squared. So that's like kilogram meter squared would be the units for I. So it doesn't very well make sense, right, to add mass, which is just kilograms, to something that has meter squared kilograms. So somewhere I've made a mistake back here. Mm-hmm. Ah. So it's right here. I'll do it in blue. I think you're right. I think that should be A over R squared. Right. Okay, I see what's messing with me. So here, if I solve that for alpha, what do I get? A over R, right? So if I divide this by alpha, if I divide by r, I have what? I have alpha over r, right? So what's alpha over r? A over r squared. So I'm not being careful about my algebra, and it got us into trouble. But good news, dimensional analysis fixed us. So this is supposed to be divided by r squared, then all is good in the world. So divided by r squared, yay. The acceleration is equal to, apparently, m2 minus m1g times g. So there you go. The acceleration, in summary, is m2 minus m1 times g divided by m1 plus m2 plus 1 over r squared times the moment of inertia for the pulley. All right? Now, the question then is, well, first of all, does this make sense? If we think back about our previous treatment of the Atwood, this is the Atwood machine, right? This is a less naive version of the Atwood machine. And, of course, the one you did in lab, the mass of the pulley was so small, it really was a pretty good model, right? Because the masses on the strings were much heavier than the pulley. So the mass of the pulley is comparatively, you know, you can ignore it. But if you look at this, what happens if they put the moment of inertia to be 0? Well, this term is gone, right? And this formula is back to the difference of the masses divided by the sum of the masses. That's what we found before. This makes good sense, the formula that we found so far. Now the question is just, what on earth is, you know, the mass of the pulley? And if I want to make this numerical, I probably should give us some values for m1 and m2. What do you want to make them? Let's say m2 is 30 kilograms, and let's say the m1 is 10 kilograms. That should make it exciting, all right? So that's going to give us, you know, 30 kilograms minus 20 kilograms times 9.8 meters per second squared divided by 10 plus 30 is 40 kilograms plus the moment of inertia for the pulley, which I'm going to just leave a fill in the blank here. We'll come back to that. We need to figure that out. Let's focus our attention now then on the remaining piece of the puzzle, which is what on earth is the moment of inertia for the pulley. So guys, how do you think we figure out the moment of inertia for the pulley? Yeah? So let me propose this. The moment of inertia for the pulley is coming from, well, 5 things. The inertia for the rim, plus the inertia for spoke 1, plus the inertia for spoke 2, plus the inertia for spoke 3, plus the inertia for spoke 4. This is really silly to have written that. What could we use symmetry to say from the start? Should the moment of inertia for each spoke be the same? Yeah, I mean, they're the same. There's really no difference between them. You could interchange them without changing the structure of the wheel. I mean, there's a symmetry there. So we could just do 4 times the inertia for one spoke, right? So really we're looking at the moment of inertia for the rim plus 4 times the moment of inertia for a spoke. So what's the moment of inertia for the rim? What is the rim? The rim is a cylinder, a cylindrical shell. I'm not sure that that's even on this. Oh, yes it is. It's part A, essentially. It's a thin hoop. You could think of the wheel as being a thin hoop. So the rim is essentially a thin hoop, and it tells us that it's mr squared. Now that's the mass of the rim times the radius squared. So this is the 2 kilogram mass is the one I'm talking about. All right. So let's say mass of the rim times radius squared. And then how about the spokes? What's the deal with the spoke? What are we looking at there? We're looking at, here's our point of rotation. We've got a rod that's rotating like this, right? So if this has length L, then the moment of inertia for a rod rotating around its endpoint like this, again, look at the table. So, by the way, is this something you need to have on your formula sheet for next test? You're like, no, that's for the week. I'm memorizing these, right? You're like, no, that's wrong. I'm going to learn Calculus 3. I'm going to learn how to derive these from scratch because it's fun. No. Okay. You guys are a difficult audience today. Let's see here. One third. Give me trouble. 1/3. I mean, these things can all be derived with Calculus 3. Trust me, it's fun. 1/3 ml cubed is, in fact, the moment of inertia for... So that's bigger, right? For the same rod, if you rotate it around its center point, we had 1/12 ml cubed, ml squared. Now we only have 1/3 ml cubed, but 1/3 is actually what? Somebody says, I'll give you 1/3 of the inheritance, and you can keep your 1/12 of the inheritance. You know, you should say, no, I think I'll keep my 1/3. You can have the 12th, right? Like, yeah, so the 1/3 is bigger. Anyway, so we have 4 times 1/3. Mass of the rim, mass of the spoke. And then L cubed. Now, what is L, though? What is L? Oh, I guess L is the radius again, isn't it? So it's the radius. I said cubed. That's wrong. It's squared. It has to be squared. Sorry. Dimensional analysis. Remember, moments of inertia should be mass times length squared.
So is that 1/3 and L squared?
Did I say a cube up there? What's wrong with me? Goodness gracious. No. Whoa. Sadness. All right. So what we got is, what was the mass of the rim? What did I say it was? 2 kilograms, right? So we got 2 kilograms. I'm going to factor out the r squared, which was 0.03 meters quantity squared. Oh, you know what? I'm not going to do that. I'm going to leave that as r squared. You know why I'm going to do that? Because we got a 1 over r squared down here, right? That will cancel the r squared. So let's leave the r squared. 2 kilograms plus 4/3 times the mass of the spoke. What was that? 0.3. So what's this work out to? 2.4? 2.4 kilograms times r squared, yeah? So we have 2.4 kilograms times r squared over r squared. Those cancel, obviously. And we almost got it. So I think this example, given the relatively small mass of the pulley, the answer is really not much different than if we neglected it, right? Because the mass of 1 and 2 is pretty big in contrast to the mass of the pulley. I think, oh man, I brought my, no, I got no calculator. Thank you. It's been a while since I used one of these. 30 minus 20. Why did I do that with a...
Why is it 20 and not 10? I think he was thinking 30 minus 10.
Oh, yeah, that's a good question. That should definitely be a 10. Thank you. Good grief. What's wrong with me? All right, so 30 minus 10 is probably something I could do in my head. 20 times 9.8. So it gives 196 upstairs, divided by what? Divided by 42.4? I get 4.623. 4.623 meters per second squared. Now, related question, what's the angular acceleration of the wheel? Or what's the angular acceleration of the pulley? Alpha, right? Which is what? How's that related to A? That's A divided by R. So what's that equal to? We would take what? 4.623 meters per second squared and divide by what? Radius was 0.03 meters. And what's that give me? Thank you. Whoa. 154.1 radians per second squared. So that little pulley, it's really spinning pretty fast, isn't it? Does this make sense, what I'm describing, this analysis? Yes, no? Right. See if I can think of another problem here for you. So, do you see the relevance to your quiz problem? Right, on the quiz I asked you to find the final velocity of a wheel with more spokes, but it's kind of the same thing, right? So to do that problem, you're going to need to figure out what's the moment of inertia for the wheel with spokes. It should come from two things. One thing should be the moment of inertia of the rim. The other is the moment of inertia for each spoke. You got to add those together to get the net inertia for the wheel spinning, right? In that, I think quiz 6, right? Last problem, quiz 2, problem 2. And but otherwise, the analysis for that problem would be similar to the one we worked at the end of last class, where we had an inclined plane and we let a sphere roll from rest down the plane and asked what the final velocity was. So that problem 2 of quiz 6 is a combination of the last example from last class and this idea of building the moment of inertia up from a sum of the pieces. All right? So now I would do more exciting examples, but unfortunately, your book doesn't think the parallel axis theorem is worth talking about, so that greatly limits the sphere of problems I can ask you. I know you're very upset about this, right? I can see the infinite sadness that's fallen upon you. It's good. No, that's not good. No sadness. All right. So you guys have any questions? No? All right. Well, next example then. Suppose you have an ice skater. And we will model the ice skater by the following model. For us, the ice skater will be modeled by a solid cylinder. Okay. And a arms, which we will use rods of length L, like that. And so let's suppose that so this is a crude model of an ice skater, and suppose that this is the initial angular velocity, let's say omega is, suppose that they're originally rotating at, let's say, 10 radians per second with their arms outstretched, right? Like so. And so this here is mass, they're an ice skater, so 50 kilograms. It's probably too much. And let's suppose that, you know, the radius of their cylindrical body is 12 centimeters. All right? And they're initially rotating with 10 radians per second. Then, all of a sudden, they take their arms and they do this. Zoop. All right? Like that. Then the question is, you know, what's their final angular velocity if they just put their arms down like that? So before, after. So arms down. So what's the moment of inertia before? And I'm going to pretend that their arms are attached to the center of their body for the sake of the simplicity of the analysis in here. Because that's all I can do because we don't have the parallel axis theorem. Dang it. I never realized how important the parallel axis theorem was until I lost it. Oh well. Anyway, moment of inertia before. So we have the moment of inertia for the cylinder plus the moment of inertia for the arm. And we've been here long enough to know that we're going to say twice the moment of inertia for one of the arms, right? So what's the moment of inertia for a cylinder? And I probably should tell you that the length of their arm is, let's say, 60 centimeters. All right? And I also need to tell you the mass of their arm. How massive should their arms be? Let's say 5 kilograms. Okay? They've been training. 10 kilograms. 10 kilograms. Yeah, sure, why not? That'll make this more exciting. 10 kilograms. Okay, so what's the moment? Yeah?
So for that, would the mass, the 50 kilograms, just be for the cylinder then?
Just the cylinder. Just the cylinder.
That's not including the weight of their arms.
That's true. So the mass. I'm saying the mass of their core, plus their legs, and their head.
And then
Each arm is 10. So their net mass would be 70 kilograms. Yeah. Which is quasi-realistic. All right. So the mass of the cylinder, rotated about the center of the axis, is in fact 1/2 mr squared. I think. I don't remember it until I've derived it, you know? And since I'm not allowed to derive it in here, it may force me to be stuck to this paper. Yeah, 1/2 mr squared is the moment of inertia for a cylinder about its axis, center axis. And then what's the moment of inertia for the arm? We just talked about that before. It's 1/3, so we have 2/3 mass of the arm, length of the arm squared. All right, so let's work it out. What's the moment of inertia here? We got 1/2 times 50 kilograms times 0.12 meters squared plus 2/3 mass of the arm, which was 10 kilograms. Let's see here, times 0.6 meters squared. Notice I'm just converting the centimeters to meters, right? So what's the moment of inertia before they put the arms in? Thank you. So I get 0.36 kilogram meters squared for the first thing, which is good because I can use that for the other calculation just the same. And then let's see here, 2 times 10 divided by 3, 6.666666666 times 0.6 times 0.6, of course. This one's 2.4. Whoa, 2.4 kilogram meters squared. So before, the moment of inertia is what? 2.76 kilogram meters squared. After, what's... Okay, so then there's one other conceptual thing we got to think through. What kind of moment of inertia does the arms down give you? What's the situation? So here's a general rule. If all of the mass is the same distance from the center of rotation, then it's just the mass times the radius squared for that kind of mass. And the whole arm, in this later situation here, both of the arms, every bit of the arm is the distance r away from the center, right? So this is plus 2 times the mass of the arm, which was 10 kilograms, times the, 0.12 meters squared. That would be the moment of inertia for the arms if they're just dangling, like so. Right, neglecting any size of the arm. Supposing it's all at the surface of the cylinder. I mean, this is an idealization, of course, but this is a decent toy model for an ice skater, I think. Let's see here. So we got what? 0.36 plus 2 times 10. So 20 times 0.12 times 0.12. That gives me 0.288 plus 0.36. I get 0.648 kilogram meters squared. All right. So what is conserved in this process? If you're an ice skater and you've got your arms out and you're whipping around at 10 radians per second, is it easy to lower your arms like this? No, it actually requires significant strength to put your arms down, doesn't it? Your arms want to whip out and do that, don't they? Right? So it takes work to bring your arms down, actually. But what is conserved, of course, but on the other hand, that's an internal work, right? I mean, there's not an external force acting on the skater, right? So if you think about the skater in and of itself, over the moment, as long as they put their arms down pretty fast, there's no external force on the system, right? Yep.
Would it be the same to put your arms up?
Yeah. Everything else being the same, if you put your arms back up after you put them back down, you should slow back down to the initial rotational speed. Of course, we're going to find out that the system speeds up, right? I mean, like it's going to, when they bring their body into a more a more narrow profile close to the center of rotation, it speeds them up considerably. If they're kind of like spread out and rotating, that's more kinetic energy because they've got a larger moment of inertia. We're doing the math at the moment, but that's the conceptual idea here. And you can see that the moment of inertia, which is the rotational analog to mass, right? In some sense, they weighed 2.76 rotational mass units, right? And then after putting the arms down, they only weigh 0.648 rotational mass units. But the thing is, in this process, angular momentum is conserved, right? So that's the thing we use, angular momentum conservation. Angular momentum before is equal to angular momentum afterwards, but that's the moment of inertia times the initial angular velocity is equal to the final moment of inertia times the final angular velocity. Here, the moment of inertia is changing, right? And so, hey, we know all these things, so we can calculate omega f. Uh-oh. There we go. See here. Let's see here. So the time is near. It's nigh upon us. Almost done. And so we got 2.76 times 10 radians per second divided by 0.648. All right, and I just dropped the kilogram meters per second because it's on both of them, and it's just going to cancel. So why bother? I guess I could bother, but anyway, this number is the final angular velocity. What would that be? Whoa, 42.6 radians per second. So if my toy model of an ice skater is anywhere near right, if they can skate around the rink and get going at 10 radians per second around their axis through whatever skating they're doing, and then they draw their arms in, it quadruples their rotational speed. I don't think that's far-fetched. If you've watched ice skaters and you watch them as they kind of go into the center and then do their thing, it does seem like they speed way, way up when they finally get into that like really tucked down, centralized position, which is lowering their, in some sense, angular mass, their moment of inertia, as much as is possible. So, now, hey, is there a way you can ask this question on a physics test and make it like a lot easier and less cluttered? It's pretty simple. All I have to do is say, suppose you have a skater who's initially rotating with an angular speed of 10 radians per second, and their moment of inertia is effectively 2.76 kilogram meters per second. Excuse me, 2.76 kilogram meters squared. And then after they tuck in their arms, their effective moment of inertia is 0.648 kilogram meters squared. Find the velocity, the angular velocity of the skater after the arms are tucked in. See, I can ask this question without making it complicated and having the cylinder and the rods. I'm just trying to educate you more about how we calculate moments of inertia through using the things on this table together. All right? Anyway, we have another whole day of this, so ask homework questions next time. Thanks, guys. Well, it's election day, so maybe we'll see each other Tuesday. I don't know. You know how it is.